Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over 6K worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians! You're listening to the podcast where math is figureoutable. I'm Pam.
And I'm Kim.
And you found a place where math is not about memorizing or mimicking, waiting to be told or shown what to do, but it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can mentor mathematicians as we co-create meaning together. Not only are algorithms not particularly helpful in teaching mathematics, but rotely repeating steps actually keep students from being the mathematicians they can be. And teachers too, to be clear.
So last week, we dove in deeply about one of our favorite models, the open number line, and one of our favorite ways to introduce it. And we also talked about why it's so valuable. If you missed that episode, you should check it out.
Absolutely.
This week, however, we are so excited to focus on another model that is important, but less discussed, and that is the double open number line.
So we did the open number line last week. Double open number line. What's that, like double the trouble? Like what is a double open number line? And I'm going to be really honest and say the first 150 times I saw a double open number line, I didn't get it. I was like, what is and I just tuned it out, turned it off. And I'll tell you where I was at that point in my life. I was developing my additive reasoning along with my young kids. And I had seen some work where people were talking about how they could use a double open number line. And I was like, whatever, weirdo. It didn't it didn't land. And in hindsight, I believe it's because I wasn't reasoning proportionally. And so because I wasn't reasoning proportionally, a proportional model, a double open number line, wasn't hitting for me. It wasn't making sense. I wasn't reasoning through proportional reasoning problems at all. And so I would look at, the problem they were solving, and I had so little access to those problems that I couldn't understand what then they were doing on a double open number line. So that we'll try today to do our best to make it accessible to everyone. But you might consider that if you're still building your proportional reasoning, that you might want to dive in and actually do these problems with us and be thinking and reasoning. Don't expect it to be just, oh yeah, of course, that's what it is. It wasn't for me. So if you're like me at all, maybe you're going to want to sort of co-create it with us as we go today.
Cool.
So how does a double open number line compare to that normal open number line? A normal open number line, like we talked about last time, is different from a closed number line. A closed number line has all of the tick marks. Every whole number has a tick mark. An open number line is where we get to choose. We put the tick marks where we want them. We sort of label the numbers that are helpful for us in solving a problem. A double open number line keeps track of corresponding quantities. So I have quantities on the top of the number line and quantities on the bottom of the number line. We still have jumps in between quantities, but I have corresponding quantities being represented. That might sound a little bit like a ratio table. And so maybe at the end of this, we'll compare a little bit ratio tables and double open number lines because they have some similarities, but they also have some differences. And it might be helpful but they both have that similarity that there's two things corresponding to each other. So to get at what we mean by that, let's actually do a problem string. So I'm going to ask some questions. Kim, you're going to tell me what you're thinking about. And then I'm going to, y'all, we're on a podcast. So hopefully I'll describe best I can what I'm drawing, what it would look like. So you can sort of see what a double open number line would look like. But this is similar to how we would introduce a double open number line to students. We would do some work. And as they tell us their strategy, we would make it visible. I mean, in this particular case, I'm going to make that thinking visible on a double open number line.
Cool.
Maybe before I forget, Kim, before we start the problem string, I will say that a double open number line is an introductory model. Let's see, how do I say this? We have talked in the past a little bit about how the area model is a brilliant model for kind of introducing multiplicative relationships and helping students really get a sense of the spatial relationships that are happening, a sense of size and magnitude and what it means to have this two-dimensional measurement thing. But when we actually want to compute with multiplication and division, we don't use the area model and open array. We tend to use a ratio table. That is actually going to be very similar with a double open number line. In my vision for models, the way that we've set up models and modeling, a double open number line is brilliant to introduce thinking proportionally, to get students to develop a sense of size and magnitude and spatial relationships and how things are related. But we don't actually expect students to then use double open number lines to compute.
Right.
And I think that's different than an open number line. An
Sure.
open number line, we actually do expect students to use a lot. But a double open number line is a little limited in some ways. And I think I'll talk about that when we get to how it compares to the ratio table. I'm just making notes. I don't want to forget. Okay, so ready, Kim?
Yep.
If you were walking, you run. I know you run, but can you walk for a minute? Or if you're
Sure.
walking, maybe you're running. Actually, I have to think about these distances I'm about to give you. Maybe you're running actually. So you're moving in some way. If you're moving around, but you're moving at a constant rate. So you're not speeding up, you're not slowing down, you're moving at a constant rate. And in 40 feet, you've moved 40 feet. So you've traveled 40 feet and you did it in 5 seconds. So you traveled 40 feet at a constant rate in 5 seconds. I'm curious, how fast were you going?
Like per second?
Yep.
Okay. So 40 feet in 5 seconds means that I'm going to go 8 feet per second.
And how do you know?
Because if I've gone 5 seconds, I wrote down 40 feet, 5 seconds, and then I divided both of those numbers by 5. Because to get from 5 seconds to 1 second is divided by 5. And so then I also had to divide 40 by 5.
Cool. And when you divide 40 feet by 5 seconds, you end up with feet per second, feet divided by seconds, which is a rate. And you're saying that you were going at 8 feet per that 1 second.
Yes.
Nice. If I was working with students, I might say, okay, so you said that you traveled 40 feet. And so I would draw a number line on my paper. And I've put 0 on the left-hand side above the tick mark. And I've put 40 feet on the right-hand side. So 0 feet on the left and 40 feet on the right. And I've actually capped those ends. So I'm not going beyond those ends. Of sort of, there they are, tick marks on either side. And then on the bottom, I'm going to put seconds. And so on the bottom, right underneath the 0 feet, I'm going to put 0 seconds. And right underneath the 40 feet, I'm going to put 5 seconds. And then I'm going to kind of model visually what you just said, because you said, well, I've got 5 seconds and I know each of those seconds I went some feet. So it's almost like you took that distance from 0 to 5 and you sort of cut it into 5 chunks. And y'all, I just cut it into 5 chunks. I'm actually getting kind of good at that, Kim. I was not
I just did it too.
To cut a distance into 5 chunks, that's tricky.
Yeah,
that's tricky. In fact, let's a little test here. How many tick marks did you draw?
How many tick marks did I draw for 5 seconds?
Yeah, so like when you said you cut it into 5 equal chunks.
4, yeah.
You only drew, so you had a beginning and ending already, but then you just drew 4 tick marks because you're trying to make 5 chunks. So that's also something that kids need to mess with a little bit. And it's one thing that we can mess with a little bit on the open number line. Definitely when we get to a double open number line, it's a thing that we're going to have to consider. Most students will draw 5 tick marks and then try to, what? or at least many students, and then try to figure out why
Mhm.
they now have 6 chunks. And yeah, anyway. Okay, so I've got these 5 chunks. And so I've labeled now on the time axis, sort of underneath the number line where I have time, I've labeled 0 seconds, 1 second, 2, 3, 4, and then that ending 5 seconds. And since I just cut the seconds by 5, it's exactly what you said. You divided the 5 by 5 to get 1 second intervals. Now I'm going to do the same thing to the 0 to 40. Oh, and 40 divided by 5 is 8. And so I could put 8 above the 1 second, and I could keep going, but I'm actually going to choose not to. I could put 16 above the 2 and so on.
Mhm.
And then I would sort of know where I was at every second. I would not take that long with students. The reason I just took so long to say that, I would just do it. I would draw it up on the board. I would fairly quickly talk about what I was doing and move on. But I took a little bit more time here because we're audio only, and I wanted to make sure everybody knew what I was drawing. Second
Yep.
problem. This time, Kim, I'm sorry, before the second problem. Hey, if you're going 40 feet in 5 seconds or 8 feet per second, what does that feel like to you? Does that walking, crawling, running?
8 feet per second?
Yeah.
Oh, I'm going fast.
It's pretty quick, right? Okay.
Yeah.
Cool. Next problem. How about if you're going 20 feet in 4 seconds? Constant rate, 20 feet, 4 seconds. How fast are you going?
5 feet per second.
How do you know?
Same thing. I did from 4 seconds to 1 second is divided by 4. 20 seconds divided by 4 is 5 seconds.
It's 5. And 20
I
divided
mean,
by 4,
20
that's
feet
not
divided by 4. Yeah.
right. And 20 divided by 4 and feet divided by second. So you end up with 5 feet per second. So very quickly, I would draw a double open number line. So I've got a line drawn. I've got 0 to 4 seconds on the bottom. I've got 0 feet to 20 feet on the top. I did draw that about half of the 40 feet that I drew before. No, that's not true. I drew it the same length. No, that's not true. I drew it. I'm asking myself if I like what I drew. I'm going to tell you what I actually drew. I actually drew it the same length as the 4 seconds. And I put the
Yes.
4 seconds down first.
Yep.
But I didn't worry about the fact that the 20 is half of the 40 feet. So the 4 seconds is right underneath the 4 seconds I had in the previous problem, even though I had 5 seconds, but I put it underneath the 4. But I have put 20 feet above that tick mark. So
Okay.
right now,
So
the
maybe
course
time be
the same.
The same. Okay.
Yeah. I may ask myself later if I'm glad I did that, but that is what I did.
Okay.
Okay. And then on the top of that open number line, I have 0 feet to 20 feet. And
Okay.
you said that same thing. You divided the 20 by 4, or the 4 by 4 and the 20 by 4. So I could divide, when you said you divided the 4 by 4, I could think about where would those 1 seconds be.
Mm-hmm.
And I would do that easier than the 5 seconds. I would cut that span that represents 4 seconds in half for 2 seconds, and then cut that span in half to get the 1 second. That's an easier cut to do. Cut in half and then cut it half again, rather than eyeballing the 5 equal chunks. And then since you divided the 20 by 4, I could also, I know that's 5, and then I just stuck the 5 above that 1. But I might ask students, hey, once we cut the 4 seconds in half to get the 2 seconds, what corresponds to that? Nudging the fact that if I cut the 4 seconds in half, could I also cut the 20 seconds in half? Sure. And so that would be 10. And once I know that 2 seconds was 10 feet, could I also then, when I cut that in half to get 1 second, cut the 10 feet in half to get 5 feet? And I'm just going to kind of bring that up, sort of try to draw that out of the student quickly, not belabor it too much, but just kind of like raise it as a possibility. Next question. How about if you moved 24 feet in 4 seconds? How fast were you moving?
6 feet per second.
And as you were thinking, I drew the same length of an open number line that I had for the 4 seconds, and I put 0 seconds to 4 seconds. And then you had already said 6 seconds. And so I might at that point say, how far were you moving?
6 feet per second.
That was your speed.
Oh, how far am I moving?
How far total? Yeah.
24 feet.
And the only reason I asked that was to give me time to write down the 0 feet and the 24 feet.
Okay.
And then I would say, hey, did anybody do the thing that we did before? Like the cut in half thing? Did anybody? And I would just look, and I would look for somebody. I would look for a spark. I would look for a glimmer of somebody saying, yeah. And then I might say, okay, so you cut the 4 seconds in half to get 2 seconds. Did you cut the 24? And I would just say just enough for them to go, yeah, that's 12. And then I go, so then did you cut the 2 seconds in half? That's 1 second. And then what's half of 12. There's another way of getting the 6 feet per second that Kim had said.
Mm-hmm.
So I'm going to notice that right now I have 20 feet in 4 seconds was 5 feet per second. And 24 feet in 4 seconds was 6 feet per second. Next problem. How about if you went 22 feet in 4 seconds? How fast were you going?
5.5 feet per second.
And I probably should have said maybe pause for a second.
Sorry.
It's okay because we didn't give listeners a very long time to think about
I'll
that.
pause.
So my bad. So is that right, listeners? Like 22 feet in 4 seconds. And Kim, how do you know? How do you know it's 5.5 feet per second?
Well, I'm a couple of things that I'm thinking about. I like that you just had me think about half of the 4 seconds is 2 seconds. So that would be half of the 22 feet, which is 11 feet.
And so I just drawn that. I've drawn 0 to 4, and I cut it in half for 2 seconds. 0 to 4 seconds. I cut it in half for 2 seconds, and I wrote the 22 feet, and then above the 2 seconds I wrote 11 feet. Okay, keep going.
And then half that again would be from 2 seconds to 1 second, and from 11 feet to 5.5 feet.
Because half of 11 is 5.5 feet.
Yep.
And so 5.5 feet is now in the corresponding spot as 1 second.
Yeah.
Nice. All right. Do you want to tell us the other thing you were thinking about?
Yeah. Well, you already gave me 20 feet per 4 seconds and 24 feet per 4 seconds. So I was thinking about how 22 feet per 4 seconds is kind of nestled in between the 20 feet and the 24 feet.
Like right in the middle.
Which it was 5 feet per second and 6 feet per second. So that would make sense that it would be 5.5 feet per second.
Right in between. Bam!
Yeah.
Nice thinking. All right, cool. Next problem. What if you had traveled 21 feet in 4 seconds?
I'm pausing.
Thank you. I was holding my breath. I was like, is she going to pause? She did. Sweet. Okay, so Kim, 24 feet in 4 seconds. How fast?
This one is 5.25 feet per second.
5.25 feet
mm-hmm.
per second. Okay, and how did you find that this time?
So this time I kind of did opposite. I looked up. I'm writing on my paper, so I looked above what I'd already been working with, and I found that I had 20 feet per second and 22 feet per second. So again, I just went right between those two answers.
The 5 feet per second and the 5.5 feet per second, you went right in between to 5.25. Cool.
Yep.
What we could say, hey, did anybody cut the 4 seconds in half? And so 21 in half. Kim, if you don't mind, what is 21 in half?
21 is 10.5.
So that'd be 10.5 feet, corresponding to 2 seconds. And then you could cut 10.5 feet in half to get the corresponding 1 second, and that would be 5.25.
Yeah.
Cool. Next problem. How about if I asked you for 23 feet? You've covered 23 feet in 4 seconds. 23 feet, 4 seconds? Thanks for the pause.
You're welcome. 5.75 feet per second.
Okay. And what was your strategy this time?
I, again, looked in between. You had given me 22 feet per second and 24 feet per second. And that was...
And that totally makes sense. And if I had not, what if we didn't have that? What if we had 23 feet in 4 seconds cold without any of the previous stuff?
Yeah, then I would definitely go halfway would be 2 seconds and 11.5 feet.
Half of 23 is 11.5.
And then half it again to get 1 second and what I say, 5.75 feet per second. Because
half of 11.5, I have to think about that a little bit. Half of 11 is 5.5, and half of 50. Yeah, that's 5.75. Yep. I honestly had to think about that a little bit. Last problem of the string. How about 27 feet? If you covered 27 feet in 4 seconds. Now, listeners, before you just go off, I might say to a class, can you solve it both ways? Could you think about, hey, we've got a bunch of stuff up here. Is there something up here that's helpful? But what if you were cold? What if like you hit this problem on the street and you didn't have anything up here? What might you do? Go ahead and solve it. Go ahead and solve it any way you want. Just curious. Go.
Okay. I got 6.75 feet per second.
Okay. How?
So I did the half the feet and half the seconds.
Okay.
thing. So I got 13.5 in 2 seconds.
13.5 feet in 2 seconds.
Feet in 2 seconds. And then I got 6 3/4 feet in 1 second. And I actually broke the 13.5 feet into 12 feet and 1.5 feet because I
In
don't
order
just
to cut it
know.
in half. Yeah.
Yeah.
So half of 12 is 6. Half of
Uh-huh.
1.5 is 0.75.
Right.
Nice chunks. Nice chunks. Yeah,
Thanks.
I like it. Cool. So why would we do a string like this? Well, for many reasons. One, as a high school math teacher, I just realized that for this entire time, I have been leaning away from my microphone. Sorry, I'm just going to tell our listeners, our editor, who happens to be my son, is really frustrated with me right now because I've been quieter for the last few minutes because every time we work problems, I lean over on the problem on the paper that I'm working on, and I just realized I was doing it. Sorry, Craig. So I'm sure, hopefully you didn't hear it, podcast listeners, because he does such a good job of like altering the sound. But I couldn't stop saying that. So there you go. Craig, you're welcome to leave this in the podcast, not cut it out. Anyway, so when as a high school math teacher, I often get students who cannot think about rate. Like, even though they should have spent a lot of middle school time figuring out what rate means, by the time I get to them, if I say something like 40 feet in 5 seconds, they're like, what? I'm like, well, how fast are you going? They're like, what do you mean? I'm like, well, in a second, how fast were you going? I don't know. Like, and then it's not about whether they know what 40 divided by 5 is. It's literally that they don't know how to conceive, how to find that unit rate. But also, now middle school teachers up in arms are like, Pam, of course my students can. I mean, when you've given them a formula and you've told them what to do, yeah, they follow it pretty well in that moment. But as soon as I get them, there's been so many more formulas thrown at them, all the things. Really, we need them reasoning about rate, because it's not just can they find the unit rate here, but can they actually reason? So I've had occasions where we've said, hey, if you're going 20 feet in 4 seconds, is that faster or slower than 24 feet in 4 seconds? And they're not sure. Or if I've gone 20 feet in 4 seconds, or I've gone 20 feet in 5 seconds. And they really have to think about it. Now, some students have had some experience with rates and they're not too bad, but a lot of students hear those kinds of questions as, I don't know what rule I'm supposed to do now. I don't know what numbers I'm supposed to plug in. Do I add? Do I subtract? Do I multiply?
Yep.
Do I divide? And you're like, think. Like that, it's not any of those things. It's like thinking. And some of you might have been listening to that problem string, and as Kim was explaining, divide 40 feet by, or the 5 seconds by 5 and the 40 by 5, you're like, just divide 40 by 5. But she's actually reasoning. She's actually like thinking through the problem, making sense of what's happening. And that's what we need in students. So A, there's a reason to do that problem string. But B, today we wanted to give you a sense and a feel for why a double and open number line, what it could look like. And so we actually have taken notes on today's problem string, and we have written up what this looks like. And so you can download what this looks like at mathsfigureoutable.com/double for double open number line. So mathsfigureoutable.com/double. You can download this problem string or one like it, and some extras, some questions to ask, and what your board could look like, what the double open number lines could look like, because we realized this was all in the air and all verbal, and we want to give you guys a chance to sort of see what it would look like. Why do we use double open number lines with students? It gives them a model on which they can operate, a way for them to think about, how can I reason about what's happening with these numbers, with the context and the situation, and it can be very, very helpful. Now, I mentioned earlier that a double open number line is similar, or has some similarities to a ratio table, just like an area model has similarities to multiplication and a ratio table. So similarly to how we want to use an area model to build spatial relationships and magnitude, then transition with multiplication division, then transition students to be using a ratio table as the tool with which to compute. The same thing is true with proportional reasoning and a double open number line. I want to use a double open number line primarily where I, as the teacher, am the one that's drawing the model. I'm representing what they're thinking with the model. I don't demand it back from students very much, because then I want to transition to having students actually use ratio tables to help them reason through most proportional reasoning problems. So just quickly, as an example, if they were reasoning about that very first problem that we did, 40 feet in 5 seconds, I would expect that eventually a student would write down sort of a ratio table looking thing where it would be 40 feet divided by, or that division line over 5 seconds. And then they would create an equivalent ratio. And they would say, oh, well, so if I'm going to divide the 5 seconds by 5, and I've literally written down like an arrow, 5 seconds divided by 5, that would be 1 second. Then I would also divide the 40 feet by 5, and that would give me 8 feet. And now I literally have a ratio of 8 feet per over divided by 1 second. And so we'd expect students to eventually get there, but it's not because we told them to do it. It's because they're reasoning about how they're finding an equivalent rate that's per 1 second. So in that way, double open number lines are a little bit limited, because let me say one other limitation. Another limitation of double open number lines is that we're sort of stuck with having to go in order. A ratio table is much more versatile because we can scale down, scale up, scale down again, scale up again, scale down, 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 scale up. In a double open number line, we have to sort of do things, or we would encourage you, if you're doing it correctly, to stay proportional. So when you've got that 0 to 4 seconds and you cut it in half, you literally cut it in half and you put that 2 seconds in the halfway mark. Again, it's because we're developing that sense of space and magnitude. And how then if we've cut that in half, if we've done that action of cutting the 4 seconds in half, then we would also cut the feet in half. It's a way of kind of helping students develop the sense of ratio and how those corresponding values multiplicatively maintain their ratio relationship, their equivalent ratio relationship. And that happens as we keep the distances making sense. But then that also limits the double open number line a little bit. It's not as easy to scale down, scale up, and do all of the thinking that we want to do in a more complicated problem. I don't know, Kim, I hope that makes a little sense, because I'm doing it all in the air. It's kind of hard to do it verbally. Cool. So double open number lines can also be very helpful in things like helping students develop the idea of a common denominator, as we can use sort of course lengths to help them. We'll do that probably. I'm just going to mention that today, that in addition and subtraction of fractions, a double open number line can again become a really helpful beginning model for us to help students sort of nudge towards that idea of what they want to use it. It's helpful to use it. So we'll probably do a whole podcast on that sometime soon. The last thing that I kind of want to end with today is a realization I had not too long ago, that a double open number line is a huge way for us to help students make sense of percents. Now, often when we do percents, we use what we call a percent bar. But in almost all the ways, a percent bar is just a double open number line, where we've just let it be. We've let that double open number line kind of have space in the middle to sort of resemble a download bar. If you think about downloading stuff from the internet, downloading a song on your phone, like whatever you're downloading, and there's this bar that sort of shows you how much you've downloaded. Well, a percent bar can look like that, but in a huge way, a percent bar is just a double open number line, where on the one side, today on our double open number line, we had time on the bottom and we had feet on the top. In a percent bar, you have percents on one side, and you have then the corresponding values, whatever you're finding the percent of, are on the other side. And you just reason the exact same way that we were just reasoning with a double open number line. And so that's kind of a cool connection. And in a huge way, that helps us understand that it's always 100%. That always is what goes on one side of the double open number line, or the percent bar. And then it's that other thing that goes on the other one, and it stays in proportion. That's the brilliance of that model. Cool. Yeah. Because rates are so important, and we need students to understand this proportionality in rates, and we can use a model like the double open number line to do that, so that when I get them in the high school, they're actually owning the idea of rates. And so that's going to be important to build in the middle school. But if you are a high school teacher, you could dump in a problem string like today to help students reason about rates of change for as you're going towards the slope of a line. You can use a problem string like we did today in the middle school to develop rate. you can use it in the high school to quickly grab some development as you then move into the content that you actually teach.
Right, and you're meeting them where they are, right? So
Exactly.
and that's exactly what we have tried to do in building powerful proportional reasoning. We use problem strings to build ratios and rates, and also in your very brand new building powerful linear functions, which is super exciting and
Woo,
brand
woo,
new.
woo.
We show them how to use them quickly right there as they're needed. So if you're a middle school teacher, you should check out building powerful proportional reasoning. And if you teach 8th grade and algebra, you need to check out the brand new building powerful linear functions, because registration is opening very soon.
And I will just say, building powerful linear functions may be my best work.
Mm-hmm.
I'm so excited about it, and it's about to open up. We've been working on it for a while. I'm thrilled. Y'all just wait until you see it. It's coming. It's coming. Yeah,
Yep.
Very excited.
Yep, people have been asking for it, and it's almost here.
Woo! So thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figureoutable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.